Delaware Tech, Chemistry 100, Chemistry 110, Acid and Base Nomenclature. So before we talk about naming the acids, let's talk about some terms we use with acids. Strong and weak. Strong acids and strong bases are strong electrolytes. In other words, these are molecules or compounds that when you put them in water, they break up into ions completely. So 100% of them dissociate into individual ions in water. That's what strong means. So all of the component ions will dissociate in the water. They completely dissociate, that's how we say it, or they completely ionize. That's another way to say it. So strong acids would include the following: hydrochloric acid, HCl, HI, hydroiodic acid, HNO3, nitric acid, H2SO4, sulfuric acid, HClO3, chloric acid, and HClO4, perchloric acid, as well as a number of others that you're not responsible for, and some other acids that you're definitely not responsible for called superacids that make these strong acids look like Kool-Aid. They are incredibly crazy strong acids, well beyond the scope of this course, but very interesting. So the strong bases will be bases that are made from alkali metals, lithium, sodium, potassium, rubidium, and cesium hydroxides, as well as alkaline earth metal hydroxides, magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. So if they're made from metals in the first two columns of the periodic table, those are strong bases. If they're hydroxides from those, strong bases. Weak acids and weak bases only partially ionize in water. They don't form many ions, so they don't make good electrolytes. They are called weak acids and weak bases. Do not confuse the term concentrated with strong, and don't confuse the term dilute with weak. Concentrated versus strong refers to how much of the material is dissolved in the solution, how much you put in the water, not how much it breaks apart. How much you put in is, so if you put in a lot into the solution, it's concentrated. If you only put a little bit in solution, it is dilute. So these terms refer to how high your molarity is, or your concentration, whatever concentration unit you're using. Strong and weak are terms that are specific to each compound. So you can have strong compounds that are not concentrated, and you can have concentrated compounds that are not strong. For example, 5 molar acetic acid. This is a very high concentration of acetic acid, but acetic acid is acetic acid, and that is a weak acid. It's an organic acid. Almost all of your organic acids are what we call weak acids. They only partially form protons, they only partially dissociate, they only partially ionize, even though it's very concentrated. This material is extremely dangerous. You have to be very careful with it, but it is technically a weak acid because acetic acid is weak. It has nothing to do with the concentration. On the other hand, 0.1 molar, that's a very low concentration, of nitric acid is still a strong acid. Why? Because nitric acid is a strong acid. When you put nitric acid in water, that HNO3 becomes H plus and NO3 minus completely. 100% of it goes and becomes those two ions in water. So if it breaks apart completely, that's strong. If it doesn't break apart completely, that's weak, and that is particular to which compound we're talking about. It has nothing to do with the concentration. So let's talk about naming acids. And the acids come in two categories. Remember when we were naming ionic compounds, they came in two versions of them. They were either cations with simple anions like oxide and sulfide and chloride and fluoride, or they were made with polyatomic ions like nitrate and sulfate and chlorate. Well, the same thing goes for acids. We have acids that are made with just hydrogen and a simple anion like chloride or iodide, and we have other acids that are made with the polyatomic ions. The first category that's just made with two kinds of atoms, hydrogen and something else, are called the binary acids. And these are inorganic acids that are quite soluble in water. They're frequently gases when they're not in water. And so in an anhydrous form, we would just use the ionic nomenclature rules, hydrogen chloride or hydrogen sulfide, etc. But as an acid, that is, once you dissolve it in water, we have a way of naming binary acids, acids with just two kinds of elements in them. We would say hydro because there's a hydrogen in it, and then we would use a root word that represents the other atom. So that's our anion root, and we would end it with ic acid. So, for example, HF is hydrogen fluoride gas, HCl, hydrogen chloride gas, HBr, hydrogen bromide gas, HI, hydrogen iodide. And these are all the anhydrous form. But once you dissolve these in water, you use the same root word that's in the name, fluor, chlor, brom, iode, and then you would put hydro in the beginning because there's a hydrogen, and ic at the end, an acid to tell you that it's an acid. So hydrofluoric acid, HF, is hydrofluoric acid. And by the way, this material is insanely dangerous. Not so much because it's very acidic, but because it reacts with parts of you. If you get even a drop on your arm or your leg, that drop will penetrate through your skin, go to the bones, and the fluorides in that molecule will react with the bone material in your limbs and literally eat it away. And as a result, even a drop on your arm or a drop on your leg will result in amputation. So you have to be extraordinarily careful wearing a full bodysuit whenever you work with HF, or either as a gas or as an acid. HCl is hydrochloric acid. You've heard me use that term. Hydrogen chloride gas dissolved in water is hydrochloric acid. So the acids are all your aqueous forms. Hydrobromic acid and hydroiodic acid. Hydrochloric acid and hydroiodic acid are both pretty strong acids, so you have to be careful working with them because they're strong acids. We also have acids made from the elements below oxygen on the periodic table. H2O is just water, which is a very weak acid, and we don't use the acid name for that. I guess it would be hydroxyic acid, but we don't use that. Obviously, we say water. If we want to be super technical, we might say dihydrogen oxide as a liquid. But H2S, this is a real acid when it's in water. Hydrogen sulfide gas in water becomes hydrosulfuric acid. And you'll notice the root is slightly different. It's not just sulf, it's sulfur. So you have to be careful with sulfur compounds. Hydrogen selenide becomes hydroselenic acid. So there the root stayed the same. And hydrotelluric acid is made from hydrogen telluride. So those are the binary acids. Let's look at the polyatomic acids. Now, these are called polyatomic because all you're taking is a polyatomic ion. You've already seen charts of polyatomic ions, and the negatively charged polyatomic ions have either a -1, a -2, or a -3 charge. If you add enough protons, H plus ions, hydrogen ions, to them to get rid of that charge, so 1 to a nitrate or a nitrite, 2 to a sulfate or a sulfite, 3 to a phosphite or a phosphate, 2 to a carbonate. In each case, you will produce the corresponding acid. And the acid names are very easy. We don't use hydro this time. All we do is we take the root from each of these, we strip off the ite and the ate, and we replace ite with us acid, O-U-S, and we replace ate with ic acid, just like we did before. So nitrite, when it has a proton on it, is called nitrous acid. Nitrate with a proton on it is called nitric acid, which you've heard me refer to before. And this one's very important, so you do need to know that formula. Sulfite becomes sulfurous acid, sulfate becomes sulfuric acid, and you'll notice there are 2 protons here. Phosphite and phosphate become phosphorus acid and phosphoric acid. You probably heard me use the terms phosphoric acid as well as sulfuric acid. Phosphoric acid, by the way, is one of 2 acids found in standard Coca-Cola. It's what makes Coke acidic. The other one is carbonic acid made from carbonate ions. So if you have carbonate, which is CO3 minus 2, and you add 2 protons to it, 2 H pluses, you get carbonic acid, H2CO3. We also have acids that can be made from any of these chlorine oxide ions that we had before. Hypochlorite, chlorite, chlorate, perchlorate. The ites get replaced with us acid. The ates get replaced with ic acid. So we have chlorous acid and chloric acid, but we also have hypochlorous acid and perchloric acid. Perchloric acid is another strong acid, so is chloric acid. You can actually buy bottles of perchloric acid as well. In fact, all the strong ones I mentioned, nitric, sulfuric, phosphoric, and chloric and perchloric, can all be purchased from chemical supply stores. The last one is acetic acid. This is a weak acid, and you'll notice there are a number of hydrogens in acetic acid, but only one of these hydrogens is an acidic hydrogen. The others are sitting on a carbon. That would be called a methyl group when you learn organic chemistry nomenclature. But the whole group together is acetic acid because it's derived from acetate ion. So only one proton comes off of the acid from the acetic acid. The other 3 are locked on very tightly to that carbon, and they will not come off unless you use some insanely powerful base to rip one off, but otherwise it's just one proton. Now, you'll notice some of these have 1 proton, some can release 2, and some can release 3. The ones that can release more than 1 proton are called polyprotic acids because there's more than 1 proton. So let's go through those. We have the monoprotic ones, the ones that release 1 ionizable proton, 1 hydrogen ion. Hydrochloric acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid. They're all strong acids. Those in red are all strong acids, and you need to remember those. Acetic acid is a weak acid. It is also monoprotic. 1 proton will come off of that. We also have diprotic acids that I already mentioned. Sulfuric and sulfurous acid have 2, as well as carbonic acid have 2. And these will come off 1 at a time, and depending on the conditions you're in, the pH that your solution is, maybe 1 will come off, maybe none will come off, maybe both will come off. So you have a total of 2. These are referred to as diprotic, 2 protons on there. And then we have the triprotic ones. We have phosphoric acid, which has 3 protons, H3PO4, and again, all 3 can come off 1 at a time, and so I don't label this as strong because each one of the protons on these have different strengths, so we're not going to include it in the strong acids. So the strong ones are all labeled with a yellow, they're in red, and they've got a yellow border around them. So those are the ones you need to know as strong acids, and just assume that everything else I give you is a weak acid. So hydrochloric, hydroiodic, nitric, chloric, perchloric, and sulfuric are your strong acids, and we'll consider the others weak acids. Weak acids are still dangerous to work with. You have to be careful, but they do not dissociate 100% in water like strong acids do. So let's look at naming bases, the nomenclature of bases. And bases come in 2 basic varieties, no pun intended. They come in 2 varieties. Your hydroxides, which are usually alkali metal or alkaline earth metal hydroxides, and they can be other kind of metal hydroxides, but these are the strong bases, the alkali and the alkaline earth metal ones. So these are things like lithium hydroxide, sodium hydroxide, potassium hydroxide. And here you're just using standard ionic nomenclature to name them. Lithium is your ion, hydroxide is your, lithium is your cation, hydroxide is your anion, and so the name of the compound is lithium hydroxide. Same for sodium hydroxide and potassium hydroxide. And these are all made from alkali metals. So these are the alkali metal hydroxides. We also have the alkaline earth metal hydroxides, the second column in the periodic table. Magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, and you notice each of these has 2 hydroxide groups. So when you're counting them, you have to realize, oh, there are 2 per compound, per formula unit, and that may change how much of a material you use during an experiment. But these are all considered strong bases. There are other hydroxides that are not considered strong bases, but these are your strong bases, the alkali and the alkaline earth metal hydroxides. And all hydroxides are easy to name. You just use normal ionic nomenclature rules. Non-hydroxide bases, these for your purposes, will mostly include nitrogen-containing compounds. Most of them are amines or related to amines, like ammonia. Ammonia is not an amine, but it is the molecule that amine compounds, organic amines, are based on. Most of these non-hydroxide bases that you'll be dealing with are organic bases. That is, they're carbon compounds that, in this case, have nitrogens on them. That is the basic part of that molecule. The nitrogen is your base part. They're all weak bases. There are very few that aren't. Those are more exotic and beyond the scope of this course. So ammonia, which is NH3, when you put NH3 in water, it will basically react with water and make NH4OH, which is essentially water added to ammonia. It's actually the proton added to ammonia to make ammonium, and the hydroxide that's left will form this ionic compound, ammonium hydroxide. So ammonium hydroxide is really just another way of saying ammonia in water. We also have organic bases like methylamines, CH3, NH2. The N part is the basic part of this. There's a lone pair of electrons in the nitrogen, so these can accept protons. Another one with nitrogen is aniline, and this is a ringed compound. It has a six-membered ring called an aromatic ring, specifically a benzene ring. If you haven't had nomenclature, do not worry about this, and you're not responsible for naming these, but you should be familiar with them after a while. And aniline has this amine group, NH2 group, sticking out of the ring, and the N is the basic part of it. It has a lone pair of electrons that can pick up a proton. And then we have pyridine. Pyridine is another ring compound, but the nitrogen is actually within the ring, and the nitrogen still has a lone pair of electrons on it and can act as a base, picking it up. Those of you that work with pyridine, you should be aware. Pyridine, you always have to be careful with any organic compound or any compound in the laboratory, but pyridine in particular, male chemists know that pyridine in excess can actually cause sterility in males, so you have to be careful. It actually knocks out sperm production temporarily and then more permanently, so please be careful when you're working with pyridine. It has a very distinct, sicky, sweet smell to it, so it's very obvious when you're smelling it. And with that, we'll stop here.